Welcome to the session on integration, finding areas. The objectives for this session are to use integration to find the area under a curve. Recall the rule for integrating kx to the power n. If f dash of x equals kx to the power n, then f of x equals k over n plus 1 times x to the power n plus 1 plus c, where n does not equal minus 1. When integrating polynomials, apply the rule for integration separately to each term. If f dash of x is the derivative of f of x for all x in the interval ab, then the definite integral is defined as integral from a to b f dash of x dx equals f of x between a and b, which equals f of b minus f of a. Let's look again at the steps for integrating definite integrals. Write the definite integral statement with its limits, as shown, then integrate and write the integral in square brackets, as shown, and finally evaluate the integral by working out f of b minus f of a. Let's also recall the discussion on the area under a curve from a previous session. The area between a positive curve, the x-axis, and the lines x equals a and x equals b is given by area equals the integral from a to b of y with respect to x, where y equals f of x is the equation of the curve. The shaded area in the diagram in yellow is this area. Let's now take a look at an example. We are required to find the area of the finite region R bounded by the curve with equation f of x equals 2 over 1 plus x and the lines x equals 0 and x equals 1. So let's solve this. We're going to begin by sketching the curves on the same graph. So here's the curve y equals 2 over 1 plus x. And here are the lines x equals 0 and x equals 1. Here's the shaded region, R. We're going to use integration to find the area of R. The area equals the integral from 0 to 1 of 2 over 1 plus x dx. This can be rewritten as shown. We're going to apply this rule in order to integrate our function. Since 1 over 1 plus x is in the form f dash of x over f of x, we can integrate it as shown. So we now have that the area is equal to 2 times ln of 1 plus x between the limits 0 and 1. And this equals 2 ln 2 minus 2 ln 1. And of course ln 1 is equal to 0. So our area is equal to 2 ln 2. We are now going to build on these ideas and look at the area between two curves. The area bounded by two curves and two lines is denoted in this diagram. So we have the function f of x and the function g of x and the lines x equals a and x equals b enclosing a region R. The area R is equal to the integral from a to b of f of x minus g of x dx. This can be rewritten as shown. Do note that we can only use this formula if the curves do not intersect between a and b, otherwise areas are going to cancel each other out. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solution. In this example, the diagram shows part of the curves y equals f of x and g of x, where f of x equals 3x minus x squared and g of x equals x squared. We are required to find the coordinates of any points of intersection of the two curves and hence find the area of the finite region R bounded by the two curves. So let's have a look at this diagram. Here's f of x, the curve in black, and here's g of x, the curve in red. So let's solve this. We're going to begin by finding the coordinates of any points of intersection of the two curves. So where are these two curves going to intersect? The points of intersection are where x squared, in other words g of x, equals f of x, which is equal to 3x minus x squared. Rearranging this equation gives us 2x squared minus 3x equals 0. And then solving this for x gives us x equals 0 or x equals 3 over 2. Therefore, the intersection points are at 0, 0 squared. We've simply plugged in 0 into the equation for g of x equals x squared, and we would of course get the same response if we'd plugged in x equals 0 into f of x. So here's our point 0, 0. Similarly, our other point of intersection occurs when x equals 3 over 2, and when we plug this into g of x equals x squared, we obtain that the y coordinate is 3 over 2 squared. So our other point of intersection is at 3 over 2, 9 over 4, as shown. We can now proceed to find the area R, since we have the points of intersection. This equals the integral from 0 to 3 over 2 of 3x minus x squared minus x squared. Tidying up gives us that the area is equal to the integral from 0 to 3 over 2 of 3x minus 2x squared dx. Which equals 3x squared over 2 minus 2x cubed over 3. Between the limits 3 over 2 and 0. Plugging in the limits gives us this expression minus 0, which equals 9 over 8. This brings us to the end of this session. If you have understood its contents, you should be able to use integration to find the area under a curve. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.